In this video, I'd like to tell you about another way of formulating the solution, the finite difference solution to this problem, where you have this differential equation and then you know two temperatures at the boundaries. So this is a way that some people find more intuitive. And notice that the way we addressed the previous matrix setup, we said we know T0 at 40, we know T5 to be 200, and so our only unknowns are four unknowns, T1 through T4. So that's why we ended up with a 4x4 matrix problem. And some people find it confusing, or at least tedious, to have to deal with the special cases at the boundaries, right? So for example, when we evaluated at I equals 1, we had to realize that T0 is a known quantity and move that value to the other side, in this case 40. And at I equals 4, we had to take T5, which is 200, and move the 200 to the other side. So there's another way to look at this, and that is that we actually pretend to not know T0 and T5. So what's actually going to happen here is I am going to write a bigger matrix problem, T0, T1, T2, T3, T4, and T5. And I'm actually going to write out the rows. So now what I did here, right here, was come up with a formula that works for arbitrary I. And notice the pattern here. You have a -1, 2.4, 2.04, and -1. You have a point on the other side. If we do not know T0 and T5, then this matrix actually continues to follow that relatively simple pattern. So I'm just going to make a placeholder here and here. And I'm going to fill in the middle of this matrix, which is actually just going to follow the same pattern that we saw in the previous matrix. So you have a -1, 2.04, -1, 0, 0. So 1, 2, 3, 4, 5, 6 unknowns. So actually we need another 0. Okay, this needs to be spaced a little better. So the next line I can say is 0, -1, 2.04, -1, 0, 0, 0, 0, -1, 2.04, -1, 0. Okay, so what I've done here is I've essentially filled out the formula for the center of my matrix, and I have not considered the fact that I know what T0 equals. I've actually just treated T0 as if it's a variable. Likewise over here, wait, oh, sorry, there's a mistake here. So this should be -1. In this line, I have not considered the fact that I know T5. So that would seem to be an unfair thing to do, but what I'm really doing here is I'm just evaluating this equation and not considering that I know T0 and T5. So there's a different way to account for the fact that I know them. So I could actually recognize, I'll use a different color, that T0 equals 40 could be considered an equation. Likewise, T5 equals 200 could also be considered an equation. I just realized I also wrote these equations here and here. So instead of actually treating T0 and T5 as known quantities, I could treat them as equations. So if I said T0 equals 40, T5 equals 200, then what I in fact have is 1 and then zeros, and I can write 40 here, and then I can write 200 here, and in fact I've just expressed the equation here as T0 equals 40, T5 equals 200, and I realize I forgot to fill in the constant terms over here. We would actually just have 0.8. So what we've done is we've taken a problem that was originally a 4x4 matrix problem, and we have changed it to a 6x6 matrix problem. But what we gain from that is a relatively simple pattern. So rather than have to think about known quantities that I have to move to the other side, I can just treat my known quantities as very simple equations. And so now this 6x6 matrix problem can be solved for T0 and T5 pretty trivially, but you can program it perhaps more easily. And so some people prefer to do things this way rather than the way I originally presented.